So, welcome to this webinar on overview of advanced DSP. Uh, the field is so vast that I don't think anybody can do full justice in 45 or 60 minutes of presentation, but I'll try to do my best and include as many topics as I can in this overview. So, let's start. So first, I'll go through the contents of this webinar. I'll be starting by motivating the topic and talking about why digital signal processing is important now in 21st century than ever before. And then we have to see the current trends in digital signal processing right now, the hot trending topics and industry which is going on. What are the various modern world technical problems that DSP tries to solve, and how exactly does it get involved with these problems? Then I'll be explaining three of the current trends branches in a little bit of more detail. So I have chosen the 5G cellular technology first, and then the smart multimedia and wearable domain, which is a very hot topic right now. We have smart watches and smart televisions and smart devices which help us in our day-to-day life. And lastly, I'll go through the details of satellite-based navigation where I'm working currently. I wish I could include more topics, but there are so many of them, but we have a time limit here. Then after that, we'll go into some fundamentals of this field and the basic topics that are required to be understood so that we can build upon them. After going through the fundamentals, I'll be taking a few of the important advanced topics in discrete signal processing. Then I'll be discussing about various career options and job roles and responsibilities that one has who wants to embark in this field. Lastly, we'll go through some of the major companies which are the leaders worldwide in developing products or provide services in digital signal processing domain. Okay, so let's start by motivating topic first. So what is digital signal processing? It's the modeling and manipulation of sequences of real or complex numbers to extract useful information, or convert these sequences into another where a different sort of information is revealed. And then we process that information for maybe making a certain decision or for extracting another useful information about the environment or surroundings that we are in, about us, and so on. Next question would be, why should one study this field of electrical engineering, and how we use this in the current world? If we look at our lives in 21st century, it's truly a digital life in the sense that we continuously generate and consume data about ourselves, other people, and our surroundings. And DSP is the powerhouse of all these activities. It's the art of making sense of these digital signals. And I'd say the two major factors which are responsible for the disruptive growth of this field are, one, we are currently living in an era where we generate tera and petabytes of data every minute and consume about the same amount simultaneously. Whether we are talking over mobile phones, giving instructions to Alexa or some device, controlling our connected smart appliances or booking cabs, we are using DSP-dependent technology everywhere. And secondly, the exponential growth of computing capability has enabled us to do more complex DSP algorithms. Recent advancement of packing more and more digital logics on smaller and smaller chips have enabled us to do complex manipulation on these sequences. And this is actually a circle. Due to the disruptive growth in signal processing technology, we have hundreds of important real-life problems which have emerged or popped up and are ready to be solved. Also, I feel that the approach to studying this field must change a little. This is no more a theoretical topic, which in the older days was finding rare applications and only in research scenarios. So we have to develop the mathematical intuition behind the concepts rather than the rigor. And people and students should be encouraged to approach this field with a top-down approach where he or she would start by thinking about the broader system design first, and then start plugging in different signal processing blocks to solve the problem and optimize the performance. So Let's so this slide gives a very brief glimpse into the various complex applications of DSP which are currently trending worldwide. So this is further a motivation towards the advanced DSP field of work. Uh, we have very extensive DSP algorithms used in communication and connectivity industry, which is the cellular smartphone market and the cellular communication, Wi-Fi industry, Bluetooth technology, and these industries are primarily dependent on DSP hardware accelerators and complex algorithms running on DSP specialized chips. I'll be talking about this in detail later in the presentation. Then we have speech and audio signal processing industry, which has DSP as its backbone, be it noise cancellation techniques, noise reduction, noise rejection techniques, and filtering the desired speech signals from a noisy background, and so on. So DSP is the key to solving all these problems. Of course, there are other ways too, but DSP provides a cheaper and simpler solution to the problem at hand. Next one would be robust navigation technology. Today, we are achieving few meters or even sub-meter accuracy in positioning. Our phone can tell whether we are on the right or left side of a road, whether we could take the slight left and enter service road or not. And if not, then the phone quickly tries to find alternative routes. All of this is possible because our GPS-enabled mobile phones and location tracking devices are running very complex DSP algorithms on the received satellite signals from space. When you start to think about it, there are lots of signal impairments or errors caused by the ionosphere and troposphere, Earth's surface and geometry, and most importantly, the timing synchronization between the mobile phone and the satellite, which is transmitting the positioning or navigation signals. All of these are taken care of by the fingertip-sized DSP processor sitting inside your phones. Now, we have started teaming up machine learning, which is another very hot and trending field, finding application everywhere with DSP algorithms to solve like plethora of technical problems. We use combination in all of these other applications, which I have shown in this slide. For example, DSP algorithms should be cleaning up and denoising the voice command, which you might be shouting from one corner of the room towards Alexa, and then machine learning would be taking this denoise the voice command and make sense of it to take certain actions, whether to change the music, change the song, make a call, or turn off some appliances, and so on. So these kind of applications where we are started to tying up machine learning algorithms with DSP. And then we have very high-end time delay estimation algorithms running on radar and sonar systems, which find applications in military and other surveillance services. It finds very important application is in aviation industry. DSP algorithms and system enables much safer and smooth takeoffs and landings of the flights that we take. We have a very hot and trending industry of wearables right now, which is popping up, and smart multimedia like smart television and smart devices, which is on boom right now. I'll be talking about this in detail later in the presentation. We have a very brand new application around the corner, the autonomous vehicles and drones, delivering people and goods at your doorsteps. A lot of research, trials, and advancement is going on in this field. DSP sits in the center of this technology. We have all these autonomous driving, like driverless or self-driving cars have a lidar stack of sensors, or we can say radar system, which is continuously pushing digital data about the surroundings, and the DSP algorithm extract critical information on them so that the cars and drones can transport safely and accurately. These cars would be connected to each other like a big network and continuously sharing information with each other, avoiding collisions and traffic jams and all. And all of this will be based on very complex DSP algorithms. So there are many more applications of DSP in the current world scenario, but I feel these are the trending applications right now and will have significant impact on our lives in the future. So I've included these some of the for some of the many DSP applications. Okay, let's go a little bit into detail of what I have discussed in previous slide. So first one would be the role of DSP in communications and connectivity, particularly cellular and Wi-Fi connectivity. Digital front ends are so once we bring the signal from the carrier frequency to the baseband, we have digital front ends which are intrinsic part of any communication system. Once the radio frequency front end, which is the chip which operates on continuous time signals, once that front end has received the signal from air interface, it passes it through different low noise amplifiers and brings it down to intermediate frequency. And then finally, the ADC block, which is analog to digital converter block, samples the analog signal to spit out discrete sequences of numbers. Then comes DFE, which is the digital front end. That comes into picture, and it does all sorts of anti-aliasing filtering, decimation to lower sampling rate, and then doing some processing on the signals like frequency and timing synchronization and parameter estimation like Doppler shift estimation due to mobility. So we could be moving with some velocity, and the waveform which is coming from the base station to our mobile will have some Doppler shift because of this movement. And this Doppler shift has to be estimated. Time delay estimation due to path propagation, because the waveform takes some time, even of the order of nanosecond. It takes that much time to reach our mobile, and so these Doppler shifts and time delays has to be uh, estimated by the mobile using DSP algorithms. Once DFE brings the received signal into baseband, there are adaptive estimation and filtering loops on these discrete samples, which keep track of changing channel. I have an illustration of how the wireless channel changes based on real life scenario in the next slide. So let's check this out. So we can see on this slide that there is a mobile which is stationary, which I have shown here. And so this may be a person standing with a smartphone, standing on the footpath and browsing something on internet or trying to book a cab. And then there is a car which is moving with some velocity, and there can be some people or person working on the internet sitting in this car. So these are pretty common everyday scenarios. Now the 5G or 4G base station is transmitting waves with useful information to these phones. And these waves bounce from different objects and geographical features like buildings, trees, mountains, and other moving vehicles. And then they reach in several distorted and delayed photocopies of the original waveform to the phones. This distorts the information by a significant scale. How significant depends on channel condition in wireless communication. This is called multipath fading, because the signal is reaching to our mobile via multiple paths, and all these paths have different attenuation gains and different Doppler shift, different time delay. They all get superimposed or overlapped in our mobile here. So the information gets distorted by a significant amount. For example, we can see that for a stationary person who is trying to book a cab standing still is experiencing a slow fading here. This is what I've shown. So the channel is changing slowly, and but the person who is sitting in the car and trying to work something on internet, the channel, if you see, because the car is moving with a velocity, the channel is changing rapidly, and this is what the mobile will be experiencing. This is these two are called. This is called slow fading, and this is called fast fading in wireless communication industry. Many advanced DSP techniques like MMSE estimation, which is the minimum mean squared error estimation of time, frequency, channel response, and then Kalman filtering on these estimates to predict how the channel will change depending on recent past, is running inside your smartphone continuously. These algorithms are mitigating channel impairments and compensating them quickly to extract transmit information. So the phones have to estimate these channel responses both the fast moving one and the slow moving one. It has to predict how the channel will be changing in the future, and then mitigate them and extract the useful information to show you whatever you are trying to do on the phone. So this industry has a very extensive application of DSP algorithms. Then let's look at another cutting edge and hot application of discrete signal processing: wearables and smart multimedia devices. We are right now surrounded by small devices which we wear on our wrists or keep them attached to different places in our home, or keep them with us all the time, like our mobile phones. These devices have lots of small sensors that keep on generating enormous digital data streams. Sensors like accelerometer, passive infrared sensors, proximity sensors, thermal sensors, or we have motion detectors, deep cameras to estimate or recognize patterns about our movement, and whether we have picked up the phone from the table or what kind of motion is going on. All these sensors are embedded in these smart wearables and devices. We have smart watches which are helping us in completing tasks faster than ever, making calls, messages, chats, taking pictures. They have a like plethora of different sensors which are pushing streams of digital signals into small DSP processors. These wearables are processing the data and providing us with useful information about us and the environment. If I take a latest iWatch, which is equipped with ECG measurements and oxygen saturation level indicator and other medical well-being oriented services. For example, for older people, it has fall detection, which will automatically make a 911 call if a person falls and is not responding for a few minutes. We already are living in this kind of futuristic world with all these DSP applications. So here I'm showing you like different sensors which are embedded in the smart watches or smart wearables, and they are gathering different sorts of signals from the environment and from our body. And then the DSP algorithm comes into picture for these signals are very noisy ones. They are not these are raw signals which are coming from the sensors, and then we have to do some noise cancellation on top of that, some noise reduction on top of that, and then we have to do the important signal detection, whether something was actually happening or it was just noise. So these kind of things we have to perform on the raw signals from the sensors. And there are several other algorithms also which will be working on these wearables. We have smart connected televisions right now, which can take voice commands and change channels and switch between entertainment platforms, which can search videos for you immediately. These televisions can talk to other Wi-Fi enabled devices and take decisions based on your surroundings, like changing screen brightness based on ambient light in the room, changing speakers, equalizers based on response of the room where they are operating, and so on. So DSP sits at the center of, at the core of all these applications. Then the last topic in the current trends, which I'll be explaining in a little bit detail, will be GNSS-based navigation systems and the kind of signal processing involved in these complex receivers. GNSS receivers are required to, first of all, detect if any satellite is visible at any point of time. And if so, then it will roughly or coarsely estimate the parameters like what is the time taken by the signal to reach the phone or the GPS receiver? What is the carrier phase or Doppler shift of the satellite? This is called acquisition phase, and it involves, as shown in the block diagram, and an RFFE, which is an approximate low pass filter. This is working on the continuous time signal. So we are not in the digital domain yet. So this processes the analog signal and then forwards it to the ADC. ADC blocks is the one which converts the analog signal to digital signal. And then we have DFE, which is a digital front end. So The DFE is, I mean, you will find DFE in all sorts of communication related, whether it's your 5G chip or your navigational chip, GPS receiver, or anything. You will find DFE, because this is the block which performs all sorts of digital filtering on your signal, denoising of the signal, and multiple stage downsampling of the signal, so that you can work or process the signal at the desired sampling rate. So I'll be I mean, this downsampling and denoising comes as a advanced topic, which I'll be explaining later in the presentation. So, so the DFE block down converts the oversampled signal to required sampling rate and implements an array of FIR filters to clean up the noisy signal. Yeah. So after the cleanup samples are after cleaning up the samples, we correlate the incoming signal with the reference PRN code. So every satellite has a different PRN code. PRN is a pseudo random noise. So every satellite has a different PRN code. So we have to correlate with that code of the incoming signal. And then we have to perform DFT, which is the discrete Fourier transform. This DFT is also a very central topic to DSP field for analyzing for mapping the time domain signals to frequency domain and back. So after DFT, we get something of sorts of energy grid. I'll be showing in the next slide. So yeah, so this is what you get. So after all those processings and the correlation, and why we are doing this is because we are trying to find out this grid, which is time delay versus the x-axis, you can say, is the time delay. The y-axis is a Doppler frequency shift, and then the z-axis is giving us the magnitude or the correlation energy of the signal. So depending upon what was the Doppler shift and what was the time delay, we will see a peak on the energy grid, and the processing of this peak is what the GPS receiver in your phone is doing continuously to track track your location. So we find out where in the grid is the peak occurring on both the axis, x-axis and y-axis, and that becomes the delay and Doppler shift estimate. And we take this estimate and keep tracking. So once you estimate these parameters, you have DLLs, which is a delay lock loop, and PLL, which is phase lock loop, to keep tracking and keep showing. So you must be aware that when you are moving in a cab or a car or somewhere, going somewhere and tracking your location on your Google Maps, so it takes some time to locate you initially, and then it keeps on tracking your movement. So this is what is happening initially. The peak finding happens, and once it happened, after that we start using DLLs and PLLs to track your motion after that. Okay, so this is also this is my current line of work right now. Currently, this is where I'm working, and it has lots of DSP applications and algorithms. Okay, let's go over the fundamental topics that forms the foundation of digital signal processing. Anybody who wants to venture into careers incorporating DSP will have to get a good grasp of over these concepts. First one would be discrete signals and systems, with a little bit of emphasis on viewing discrete signals as vectors and understanding properties of a typical discrete system. Then the natural topic which would follow will be Fourier analysis of discrete sequences. This is the backbone of this field of study. We need to understand how we can map time domain discrete sequences to discrete frequencies and back. Okay, once we have understood the above topics, we have to get our head around Z transform of discrete sequences. This particular topic enables us to analyze discrete systems transfer function, which is basically the input-output relation between the of the discrete system, and especially their stability criteria and conditions. The concept of bounded input and bounded output stability is very much central to discrete system design. Understanding poles and zero in Z plane and how they can be interpreted visually is important. And then I'd like to go into some details of the implications of sampling a continuous time signal. We will try to understand sorts of questions like what happens in frequency domain when a band limited signal is sampled at some frequency fs, and so on. This will mark the completion of fundamental topics in digital signal processing, and we will then go into some of the advanced topics. uh, okay, so now when I say advanced topics, there could be n number of advanced topics that one can include and talk about. But I have chosen those topics which I have felt were important in the industry in my experience. I have experience solely in communications field, both wired and wireless. But I can say this communication industry is quite rich in DSP application and extends its reach on all sorts of advanced DSP algorithms and signal processing techniques. So one of the most important topics which finds its application in multiple industries is multi-rate signal processing. It can be very wide. It has a very wide application in audio and speech processing industry, the wireless and broadband communication industry, satellite navigation and satellite communication in general has multi-rate signal processing blocks in their front ends. So we will go over that. After that, we have to touch upon the FIR filter design principles and IIR filter design principles. So FIR stands for finite impulse response, and IIR stands for infinite impulse response. So what are the different types of design methodologies and their advantages and disadvantages and complications is what I would like to talk about. This would be a good time to talk about some filter architecture principles like CIC filter design for interpolation and decimation in general, FIR filter implementation and IIR filter implementation, and what are the different filter structures that are used in industry to design these or implement these filters. Then we will talk about stochastic signal processing over time. Over time, I have felt that this is central to any DSP work in real life application. I mean, what we encounter in real life is never deterministic or known beforehand. It's always a stochastic process. The signals, incoming signals, are always associated with some probabilistic or random nature or some probabilistic distribution. In the industry, we need to look at sample discrete sequences as stochastic processes and then study their interaction with digital systems. So, for example, the received samples on a GPS device would be a white noise process, and then by processing the signal, we would detect any particular navigation satellite of the GPS cluster, and then track that satellite for location coordinates, the latitude and longitude, and so on. So the pseudo-random sequences used in navigation signals are called have wide sense cyclostationary properties. And in order to better understand the processing on them, we have to get a good understanding of stochastic signal processing. Okay, enough on stochastic signal processing. The next topic in line would be adaptive signal processing. This is another advanced topic which finds a wide application in all sorts of real life scenarios where the system dynamics and environment is changing with time. So DSP blocks need to adapt accordingly. I would be showing a graphical implementation of Wiener filter implementation for denoising a discrete speech signal. Wiener filters are very widespread for denoising signals, where we are estimating the PSD of noise and the PSD stands for power spectral density. So the PSD of noise and PSD of signal. I'll show how. This would complete our discussion on technical concepts, both the fundamental and the advanced ones. So this is what I plan to take. Let's start with the discrete signals. We have to think about discrete signals as vectors of complex or real numbers. These are like entities which live in vector spaces. Vector spaces of particular interest to us, I mean, as practical DSP engineers, will be interested more in spaces of square summable sequences. Such vector spaces are called Hilbert spaces. I mean, don't get intimidated by the mathematical or technical terms and jargon. It actually just means that these discrete signals or vectors have finite magnitude. That's it. This is very desirable for real life application. We can further classify the signals into three broad categories. First one, finite length signals, infinite length signals, and periodic signals. Infinite length signals also occur in, it's not like we only encounter finite length signals in real life. There are situations where we encounter infinite length sequences in practical problems. For example, the continuously coming streams of discrete values through some sensor would practically mean that an infinite length signal is going into the system. There can be another classification of discrete signals, like we can have energy signals, which all those signals which have finite energies. Energy in discrete domain is basically L2 norm, or magnitude squared of the vector. So if we have a n-dimensional vector, and if we take the magnitude of that vector and square it, that's what defined as the energy of that signal. And then there are power signals, sequences which have finite average energy over time. For example, any periodic sequence will have a finite power measured over one period of that sequence. So once we have understood discrete sequences as vectors, then we can apply all those tools available from linear algebra and matrix analysis. We can then start looking at cross correlation of two sequences as projection of one vector on delayed versions of another vector. Then we can bring the understanding of orthogonal basis of a vector space that will help us in understanding different linear transformation which are done in DSP domain. These transformations reveal different information about the signal. We will talk about that when we are talking about the Fourier analysis of the discrete sequences.